All right, let's take a look at decision trees. These are very simple machine learning models. They're just basically a series of if-then statements, the easiest to understand. So let me go here, and I'll just make a new notebook. And by the way, I think 103 is fixed. If you refresh the page, I think that'll work better now. But anyway, this one here is going to show you another famous standard machine learning practice database of irises. Uh, Somebody measured the length and width of various parts of irises and of three different species. And the task is to take 50 examples of each type and sort them into the correct species based on measuring two parameters of like the petals and other properties of the iris. So there's petal length and petal width. There's a third measurement we're not using. And so this is a decision tree. It is fitting it, the iris data, and what it's doing is it takes petal length and makes one if statement. If that's less than 2.45, you go here. Otherwise, you go here. Here are the three different categories of irises: setosa, versicolor, and virginica. And the Gini measure of disorder is like entropy. It tells you how perfectly you have sorted these into all in one class. So in this case, after one if-then statement, we've got all 50 of the ones in setosa completely separated from the others. So that's a Gini of zero, zero disorder. In the original state, we have a Gini of 66.66 because we have three classes with 50 representative of each class. So this is maximum disorder. They're mixed. Now over here, we've got two categories. One of them has been removed, so Gini's down to 0.5. Now with the next decision, based on the petal width, you're able to sort them, but not perfectly. Here you have 49 of one category and 5 of the other. Here you have 1 and 45, so you see the Gini does not go down to 0. So this is a decision tree of depth 2. You have two if-then statements in a row. All right, and now you can display the predictions also in a graphical way to see the decision boundary between the two categories. And so we have one of the measurements here and the other measurement there. The first if statement completely separates these. The next if statement imperfectly separates those two, but this is the best you can do with only two layers of if statements. So the next thing is to change the depth. The max depth was a parameter up here. There it is. So if I change it to 3, so I'm allowed to have another layer of decisions, then my tree will grow a third layer here. And when I show the decision tree, it's now got a more complicated shape, so it's more perfectly separating them, and so on. All right, so now let's try using this to predict to do a curve fit. So we'll need a curve. Here's the same curve we used before, 0.1 times x times cosine of x plus noise. All right. So you get a tracing out of a complicated looking curve. Now we can fit that with a decision tree. All right, and here's a decision tree of depth 2 to do that. And as you might imagine, a decision tree of depth 2 is not going to be able to follow that complicated shape very well at all. And there you can see it is a very, very crude approximation of following the curve. So we need more depth. So let's take it to depth 6. Now this tree structure is quite a bit more complicated. All right. And if we plot it, now we've got a better approximation. You can see it's just flat because the if-then statements just take regions and make them equal. So you've got always have this quantization thing. And if you remove the max depth it will just have unlimited depth. It will go until further decisions do not improve the purity. It will maximize it. So this diagram becomes very complicated, almost impossible to see. But this one should be readable. And there you go. And this is what I was talking about overfitting. Now it has so many decisions, it spikes every data point to make the error essentially zero. But clearly this is overfitting. It's fitting these particular noise in these samples exactly. It's not just fitting the trend. So that's overfitting. All right. So that's what a decision tree does, a single decision tree. Let me stop this one.